This video shows the solution in case there is no point of interest when solving for the function of the best fit quadratic curve given a dataset. Welcome to Numerical Solutions to C Problems. The approximate approach of curve fitting needs to minimize the errors, if not zero it out. And with this method, the concept is to have the positive errors balance out with the negative errors so they can cancel out. The definite algorithm of group averages starts by dividing the dataset into two tables. In case there is an excess pair of coordinates, the first table would absorb it. Next is to take the summation of the x and y values in order to solve the average of each variable. Having an average x and y values, place them into the slope-intercept format of a linear function. Then through simultaneous equations, solve for a and b. Then again, these variables are placed into the required function. Just the same, we will be solving for the best fit line and best fit curves for the given dataset. So starting with the best fit line, we divide everything into two, and the excess will be placed into the first table. The first group has x from 0 to 6, having 5 data points, and the second group has x of 7.5 up to 12 with 4. When solving for the total, x from the first table is 15 and y is 173.55. From the second table, x happens to be 39 and y is 370.8. Now take the average. So from the first table, average x is 15 divided by 5, which is 3. Y average is 173.55 upon 5, which is 34.71. From the second table, there is 39 all over 4, which is 9.75. And y average is 370.8 upon 4, which is 92.7. With the averages already known, the functions involved are 34.71 as equal to 3a plus b. Then from the second table, there is 92.7 as equal to 9.75a plus b. The following functions are then solved simultaneously in order to have the values for the variables a and b. Manually, subtract them to have negative 57.99 as equal to negative 6.75a. So a is then solved as 8.5911. This value is then placed into any of the functions to look for b. If we use the function from table 1, we get 34.71 as equal to thrice of 8.5911 plus b, where b is solved as 8.9367. Have these values placed into the linear format to have the function of the best fit line as y as equal to 8.5911x plus 8.9367. Let's then determine the best fit quadratic curve for the dataset. And as stated earlier, what if there isn't any specified point where the curve should pass? The usual point taken is the simplest, but then do not take x off 0. It is because when 0 is placed in the quadratic equation, this becomes 0.2 as equal to a times 0 squared plus b times 0 plus c, where the first two terms are cancelled out, and c is equal to y. Thus, don't take x equal to 0 for the point where the curve should pass. This then means that we take the one next to it, and that is with the coordinate pair of 1.5 and 24.5. The first table then contains a column for capital X, which is equated to x plus 1.5. Then capital Y is equal to y less 24.5 all over x minus 1.5. So complete the third column following the function, and also the fourth column, and also note that capital Y for the second data point is taken as 0, because that data point is where we will let the curve pass. Now take the total for both variables. Capital X is summed up as 22.5, and capital Y is 41.25. The average is then 22.5 over 5 or 4.5 for capital X, and 41.25 over 5 or 8.25 for capital Y. So with these averages, the first equation is 8.25 was equal to 4.5a plus b. Look for the second equation with x values from 7.5 to 12. Fill out the column for capital X and also the values for each data point under capital Y. Take total x as 45 from 9 plus 10.5 plus 12 plus 13.5, and total y as 33.1388. These are then divided by 4 to have the average. So average x is 11.25 and average y is 8.2847. The second equation is then 8.2847 as equal to 11.25a plus b. Simultaneously use the two functions to look for a and b. If done manually, subtract them to have negative 0.0347 as equal to negative 6.75a. By dividing everything by negative 6.75, a is solved as 0.0051. By substituting this value into the functions, we find b. We use that from table 1, giving 8.25 was equal to 4.5 times 0.0051 plus b, and b turns out as 8.2271. Now solve for the last variable c from the quadratic function, where point 1.5 and 24.5 is plugged, giving 24.5 is equal to a times the square of 1.5 plus b of 1.5 plus c. A and b are also substituted into the function, making it 24.5 as equal to 0.0051 times 1.5 squared plus 8.2271 times 1.5 plus c. C is then 12.1479. The quadratic function of the dataset is then y of 0.0051x squared plus 8.2271x plus 12.1479. Lastly, take the best fit exponential curve this time, with the first table, which includes x of 0 to 6. The logarithm of y are then placed in the table. Then we take the total to solve for the average later. The total of x is 15, and capital Y total is 5.7477. By dividing these by 5, we take the average, which turns out as 3 for x and 1.1495 for y. So the function from this table is 1.1495 as equal to 3a plus b. The next table will be completed just the same as the first. So complete the third column by taking the logarithm of y for the 4 data points. Take the total of x, which is 39, and total of y as 7.8504. The average of both parameters are also computed, and those are x of 9.75 and capital Y of 1.9626. The second function is then 1.9626 as equal to 9.75a plus b. Again, solve the two functions simultaneously. By subtracting them, we get negative 0.81305 as equated to negative 6.75a. So a is then determined as 0.1205. But then, the next is to transform this value into the a for the equation, and that is using the Euler's number raised to capital A, which is 0.1205. So a is 1.1281. We then solve for b using the first function, which is 1.1495 as equal to thrice of 0.1205 plus b. Capital B is then 0.788. But small b is then e raised to 0.788, which is simplified as 2.199. Thus, the function of the best fit exponential curve is y as equated to 1.1281 raised to x by 2.199.